Good evening. Welcome to Deep Sleep Manufacturing. Tonight, we embark on an extraordinary journey through one of humanity's most monumental engineering achievements, the construction of a large-scale hydroelectric dam. This is engineering on a scale that transforms landscapes, redirects rivers, creates lakes, and generates electricity for millions of people. It is work that takes years, involves thousands of workers, and requires solving problems of almost incomprehensible complexity. Our journey takes us to a river valley where a new hydroelectric dam is being constructed. The project will create a reservoir spanning 40 kilometers, generating over 1,000 megawatts of electrical power. The structure itself will be 180 meters tall and nearly 2 kilometers long. When complete, it will be one of the world's significant hydroelectric facilities. But our story begins not with construction, but with site selection and planning. Years before the first shovel moves earth, engineers and planners conduct exhaustive studies to determine if and where a dam should be built. The site selection process begins with hydrological analysis. Engineers study the river's flow patterns over many years, sometimes over decades. They measure water flow continuously through different seasons, different weather patterns, and different years. How much water flows during the wet season? How much during the dry season? What is the average annual flow? What is the maximum flow ever recorded? What is the minimum flow? This data is collected meticulously. Historical records are examined. Sometimes records extend back 100 years or more, allowing engineers to understand long-term flow patterns. Tree rings and trees beside the river provide information about historical water levels and flood patterns. Sediment cores from the riverbed reveal information about historical flows and flood events. The hydrological analysis is critical because it determines the dam's capacity and its power generation potential. A dam in a river with high flow can generate tremendous power. A dam in a low-flow river generates less power. Understanding the water availability is fundamental to the entire project. A survey team arrives at the proposed dam site, conducting detailed hydrological measurements. They position stream gauges, instruments that measure water flow. The gauges are monitored continuously, recording the precise flow rate at different times of day and different seasons. Stream gauge 1 is showing flow rate of 1,250 cubic meters per second. An engineer reports into his recorder. This is baseline dry season flow. We'll continue monitoring through the wet season to establish the complete range. Geological surveys are conducted with extraordinary care to understand the foundation rock where the dam will rest. Boreholes are drilled to depths of hundreds of meters. The drilling progresses slowly but methodically. As the drill penetrates deeper, rock samples are extracted periodically at specific intervals. A drill rig operates continuously, boring into bedrock. The rotating drill bit grinds through different rock layers. The sound is a deep, rhythmic drilling sound as the drill advances. Every 10 meters, the drilling pauses. Rock cores are extracted, cylindrical samples of rock that provide information about the geology at that depth. A geologist examines each core carefully. The cores reveal the complete geological history of the site. The surface layers might be soil and weathered rock. Deeper layers might be different types of rock: granite, basalt, limestone, sandstone. The geologist documents the depth and thickness of each layer. Core from 50 meters. Granite with minimal fracturing. Excellent foundation rock, the geologist notes. Core from 100 meters. Granite with a few fractures but overall excellent quality. Foundation rock is strong at this depth. Rock strength testing is performed on the extracted cores. The cores are subjected to compression tests, mechanical tests that determine how much pressure the rock can withstand without failure. The tests inform engineers about the dam's foundation capacity. Compression test on granite core. Failure at 320 megapascals. This is excellent strength. The foundation can easily support the dam's weight, a laboratory technician reports. Environmental impact assessments are exhaustive and thorough. How will the dam affect fish populations? Fish species that migrate up and down rivers to spawn will be blocked by the dam. Mitigation measures must be designed. Fish ladders that allow fish to pass around the dam. How will the reservoir affect local ecosystems? The inundation of forest and grassland will destroy existing habitats. Alternative habitats may need to be created. What farmland will be inundated by the reservoir? The 40-kilometer-long reservoir will inundate significant agricultural areas. Crop loss projections are calculated. Farmers who lose their land will need to be relocated and compensated fairly. How will local communities be affected? Settlements near the dam site may be partially or completely inundated. Communities will need to be relocated. The social impacts of relocation are significant. People lose their homes, their communities are disrupted, their livelihoods change. The environmental and social studies take months or even years. Biologists survey the flora and fauna. Anthropologists study the affected communities. Engineers calculate environmental flows, the minimum water flow needed to support ecosystems downstream. A survey team arrives at the proposed dam site. They're equipped with sophisticated instruments, laser theodolites, GPS equipment, and digital measurement systems. The team will map the terrain with extraordinary precision. Every rock outcrop, every slope, every natural feature is documented with millimeter-level accuracy. The team positions their theodolites on sturdy tripods. The instruments are adjusted to be perfectly level. Laser light bounces off reflective prisms positioned across the valley. The distances are measured to millimeter precision. Elevation changes are recorded with extraordinary accuracy. The team works methodically, establishing a three-dimensional map of the entire valley that will eventually be inundated by the reservoir. The surveying process is meticulous and patient. The team may spend weeks at a single site, ensuring that all measurements are captured correctly. The surveyors understand that any error in the initial survey could propagate through the entire project, leading to problems years later. As weeks pass, the survey is completed. Digital models are created showing the exact topography of the valley. Engineers use these models to calculate the volume of water that will be impounded. This is critical for determining the dam's cost and capacity. The surface area of the eventual reservoir is calculated. The maximum depth of the reservoir is determined. Countless other parameters essential to dam design are derived from the survey data. The survey data is so detailed that it can be used to calculate not just the water volume, but also the volume of earth that must be moved during excavation, the surface area that will be affected by the reservoir, and the slope angles of the reservoir banks. After months of comprehensive study, planning, and analysis, the decision is made. The dam will be built at this site. The site has excellent geology. The hydrology supports significant power generation. Environmental impacts can be mitigated acceptably. Communities can be relocated and compensated fairly. Construction is approved to proceed. Construction cannot begin until the river is diverted from the dam site. A dry area where the dam will be built is essential. The creation of this dry area involves massive engineering effort and careful planning. The first step is detailed design of the diversion system. Engineers must calculate the maximum water flow the system will need to handle. They must design structures that can reliably carry this flow without failure. The diversion must be designed for the largest flood event likely to occur during the construction period. Typically, a 100-year flood event is the design standard. The design team creates detailed engineering drawings specifying every element of the diversion system. Concrete pour schedules are created. Equipment requirements are calculated. Timeline estimates are developed. The planning is exhaustive. Nothing can be left to chance. The first step is building a diversion dam, a temporary structure that redirects the river around the construction site. This diversion dam is much smaller than the permanent dam, but it must be substantial enough to handle the river's full flow during the wet season. The diversion dam is designed to be temporary. It will be removed after the permanent dam is complete. Workers and equipment move to the site. Bulldozers begin clearing vegetation and removing soil from the proposed diversion dam location. The earth is moved in massive quantities. Excavators bite into the earth, scooping out material. The excavator buckets are impressive. They can scoop out tens of cubic meters of material in a single cycle. Dump trucks arrive constantly, backing up to be loaded with excavated material. The trucks depart, transporting the material to a disposal area. The sound of site preparation is constant and varied. Excavator buckets bite into earth with a grinding sound. Diesel engines roar as equipment strains under load. Dump trucks beep as they back into position. Heavy machinery moves earth, creating a landscape of activity. The diversion dam is constructed of compacted earth and rock. Bulldozers push material into place. The material is not random, it's carefully selected and graded. Larger stones are often placed as the core of the diversion dam, providing structural strength. Finer material is used on the exterior surfaces. Compacting equipment operates continuously. Vibratory rollers, heavy equipment with vibrating mechanisms, compress the material. Each pass of the compacting equipment reduces the material's volume, increasing its density. The material is placed in layers. Each layer is compacted to a specific density before the next layer is added. The compacting process is critical. If the material isn't compacted sufficiently, the diversion dam could fail when water pressure is applied. The density must be verified through testing. Samples are extracted and tested to ensure the specified density has been achieved. Layer 15 of the diversion dam completed. Density testing shows 95% of theoretical maximum, within specifications. Proceeding with layer 16, a quality control technician reports. The diversion dam is completed over several weeks. It forms a substantial barrier across the river valley. The river's water, which previously flowed straight ahead, is now redirected around the construction area through specially designed channels. Diversion tunnels are being constructed simultaneously with the diversion dam. These tunnels, large enough to allow the full river flow, bypass the dam site entirely. The tunnels are bored through rock on either side of the river valley, completely separate from the eventual dam structure. They will carry the river water around the dam site for the years of construction. A tunnel boring machine begins working on the first diversion tunnel. The machine is positioned at the tunnel entrance. The cutting wheel, a circular face studded with carbide cutters, rotates continuously, grinding through rock. The excavated material is conveyed through the machine to the surface. The tunnel advances slowly but relentlessly. The boring progresses meter by meter. Every meter of advancement requires removing approximately 70 cubic meters of rock. The progress is measured daily. Advanced today, 13.5 meters. Total advanced to date, 347 meters. Estimated breakthrough in 328 days at current rate. The tunnel boring machine is a technological marvel. The machine maintains perfect alignment through the rock, using laser theodolites for guidance. The cutting wheel is automatically adjusted to maintain consistent pressure on the rock. The excavated material is automatically conveyed to the surface. As the boring machine advances, segmental concrete rings are installed behind it, forming the permanent tunnel structure. These rings, curved concrete segments, are assembled into a complete circle, supporting the tunnel walls and preventing collapse. The tunnel boring progresses for months. The machine creates a continuous tunnel through hundreds of meters of rock, completely beneath the surface. The work is continuous. The machine operates 24 hours per day. The sound of the boring machine, a deep, steady rumble, is the persistent background noise of the operation. The tunnel breakthrough occurs months later. The machine has successfully bored through hundreds of meters of rock, creating a passage that will carry a significant portion of the river around the dam site. The engineers celebrate quietly. The breakthrough is significant but expected. The breakthrough face is carefully excavated, opening the tunnel fully. Water diversion gates, massive structures controlling water flow, are installed in the diversion tunnels and in the temporary diversion dam. These gates are enormous steel structures, sometimes several meters thick, capable of stopping water flow completely or allowing controlled flow. The gates are tested extensively before being placed in service. The gates are opened and closed repeatedly. The operation must be smooth, reliable, and controllable. Gate 1 raised at normal speed. No binding. No resistance. Operation smooth. Gate 1 approved for service. Engineers carefully adjust the diversion gates to redirect water gradually. Water is not diverted all at once. That would create shock waves and potentially damage structures. Instead, water is gradually diverted from the main channel over a period of days or weeks. The moment arrives when the river is effectively diverted. The main channel that flows through the eventual dam site is now essentially dry. The rock on the river bottom is exposed. The bedrock where the dam foundation will rest is now visible and accessible. Workers immediately begin preparation of the exposed riverbed. The surface rock must be cleaned of all loose material and assessed for any unexpected flaws. Workers use high-pressure water jets to clean the rock surface. The water spray creates a refreshing mist that echoes off the exposed rock faces. The sound of the pressure washers is a steady hissing as water hits rock and debris is removed. Geological assessment intensifies now that the bedrock is accessible. Engineers and geologists walk the exposed riverbed, examining the rock carefully. Any cracks, faults, or areas of weakness are carefully documented. If significant defects are found, remedial measures are planned. Grouting, injecting cement into rock fractures, may be performed to strengthen the rock. Exposed bedrock shows excellent quality. No unexpected defects detected. Occasional fractures are filled with grouting. Foundation preparation excellent, a geological engineer reports. The diversion is complete. The river is flowing around the construction site through tunnels and temporary structures. The dry riverbed awaits the monumental task of dam construction. The site preparation has taken weeks or months, but the careful preparation ensures that the construction that follows will proceed smoothly. With the main river diverted, a cofferdam is constructed, a temporary barrier that completely isolates the dam site from any water. This requires construction of substantial earthen structures on both sides of the eventual dam location. The cofferdam must be designed to withstand water pressure from the diversion dam and any groundwater in the excavation. Cofferdam construction begins with excavation. Massive amounts of earth and rock are removed, creating the dam excavation site. The excavation is enormous in scale, extending hundreds of meters along the river valley, descending dozens of meters below the eventual dam foundation level. The excavation plan is detailed and complex. The excavation must proceed in phases to maintain stability. Equipment cannot simply dig out the entire area at once. The excavation walls would collapse from the weight of surrounding material. Excavators work continuously. The mechanical buckets dig into the earth, scooping out material in large quantities. Each bucket can hold tens of cubic meters of material. Dump trucks arrive constantly, backing up to be loaded. The trucks depart with their heavy loads, transporting material to designated disposal areas. The sound of excavation is constant and varied. The mechanical grinding of excavator buckets cutting through earth. The hydraulic hissing of the excavator machinery. Diesel engines roaring at full load. The reverse alarms of dump trucks. The crash of material landing in truck beds. These sounds blend together into the constant background noise of heavy construction. As excavation deepens, the exposed earth banks become taller and more visible. The excavation walls expose geological history, different colored layers of soil, sand, gravel, and rock. Stripes of different materials are visible, each representing a different geological time period and different conditions during deposition. The excavation creates its own landscape. Steep banks are exposed where the earth has been removed. Rock layers are visible in cross-section, telling geological history. Temporary roads are cut into the excavation walls to allow access and egress for equipment. As excavation deepens further, it approaches the water table, the level at which the ground becomes saturated with water. At this point, water begins appearing in the excavation. The water must be removed to maintain a dry working environment. Sophisticated dewatering systems are installed. Large capacity pumps, powered by diesel engines, continuously remove groundwater from the excavation. The pumping is necessary and relentless. If the water level rose to the point where it equaled the water table level outside the excavation, water pressure would push groundwater into the excavation faster than it could be pumped out. The excavation would flood and construction would be halted. The pumps operate continuously. Large pipes carry water away from the excavation site. The pumped water is either discharged into the river downstream of the dam or into surface channels. The discharge must be managed carefully to prevent erosion of surrounding areas. Dewatering system operating at capacity. Pumping rate 3,000 cubic meters per hour. Water level in excavation 5 meters below target. System nominal, a dewatering technician reports. The sound of the pumps is constant, a deep mechanical rumble combined with the flow of water through large pipes. The sound becomes part of the background atmosphere of the construction site. Dewatering wells are drilled around the excavation site, deep boreholes that allow water to be removed more efficiently. Some wells use well points, very small diameter wells positioned close together that collectively handle tremendous water volumes. The well point systems look like a forest of small pipes, but they're extremely efficient at removing large water volumes. The excavation walls require stabilization. As soil is removed, the remaining earth banks become unstable. The banks are under stress from the weight of surrounding material and from water pressure. They must be supported to prevent collapse. Temporary structures, sometimes steel sheet piling, sometimes temporary reinforced earth structures, sometimes simple earth berms, stabilize the excavation walls. Sheet piling installation is detailed and meticulous work. Long steel sheets are vibrated into the ground. Vibrating pile drivers, heavy equipment with pneumatic or diesel hammers, provide the vibration. The sheets are vibrated in overlapping rows, creating a continuous wall. The vibrations necessary to drive the piles into the earth create a distinctive sound, a mechanical rumble combined with high-frequency vibration. As the excavation deepens, more sheet piling is installed. The excavation becomes increasingly fortified as the walls become higher and more prone to failure. The sheet piling extends from the top of the excavation wall down to bedrock, creating a complete barrier that prevents water from infiltrating the excavation. The excavation gradually reaches its final depth. The bedrock that will support the dam is now fully exposed. The excavation walls extend far above the excavation floor, creating a massive canyon. The scale is impressive. Workers appear tiny against the enormous walls. The excavation is hundreds of meters long, hundreds of meters wide, and 80 or 90 meters deep. Final excavation cleaning is meticulous and time-consuming. Any loose rock is removed from the walls. The rock face is cleaned using high-pressure water jets. The rock surface is assessed for stability. Bolts are sometimes installed in the rock face to hold any loose blocks securely in place. Quality control is continuous. Measurements are taken to verify that the excavation walls are at the correct angle and location. Any deviations from the design are documented and corrected. The cofferdam is completed when the excavation is finished and fully stabilized. The dam site is now completely prepared and isolated from water. The bedrock foundation is exposed and clean, ready for dam construction to begin. The preparation phase, which has taken weeks or months, has been meticulous and thorough. Nothing has been left to chance. The stage is set for the massive task of dam construction. A large-scale dam requires enormous quantities of concrete. The dam being constructed in our story will contain approximately 3 million cubic meters of concrete. This is an absolutely staggering quantity. To provide context, it would require approximately 100,000 truckloads of concrete to be transported if using conventional trucks. This would take several years of continuous trucking. No conventional delivery system can handle this volume in a reasonable time frame. To manage this extraordinary scale, a concrete batching plant is constructed at the dam site. This is not a small operation. It's an industrial facility specifically designed to produce massive quantities of concrete continuously, day and night, without interruption. The batching plant includes enormous storage silos for cement. These cylindrical towers, sometimes nearly 100 meters tall, can hold thousands of tons of cement. The silos are installed at the batching plant location. Separate silos store aggregates, sand and gravel, in different sizes. The sizes matter tremendously. Fine aggregate, sand, and coarse aggregate, gravel in various sizes, have different properties and different uses in concrete. Cement arrives at the batching plant from the cement factory via truck or rail. Cement trucks arrive daily, sometimes multiple times per day. The trucks are specially designed. They have pneumatic systems that blow the cement powder from the truck into the storage silo. The process is efficient but creates significant dust. The cement facility installs dust control systems to minimize air pollution. Cement storage at 70% capacity. Daily consumption, 800 cubic meters of concrete. Cement consumption, 240 tons per day. Current cement inventory, 12 days of supply. A plant supervisor monitors and reports. The concrete mix design is critical and scientific. The dam concrete must have specific properties: strength, impermeability, durability, and low heat of hydration. Low heat of hydration is important because the concrete generates heat as it cures. In massive dams, the internal heat can crack the concrete if not managed carefully. The concrete mix consists of cement, the binder that hardens, sand, fine aggregate, gravel, coarse aggregate in various sizes, water, various chemical additives that modify concrete properties. The proportions are precise. Too much cement makes brittle concrete that cracks easily. Too little cement makes weak concrete that doesn't achieve design strength. The water content is equally critical. Too much water makes weak concrete. Too little makes concrete that's difficult to work with. The batching process is highly automated. Raw materials are measured precisely using electronic scales. The scales are calibrated regularly to ensure accuracy. Sand is measured to the nearest kilogram. Gravel is measured in specific size fractions. The cement is measured with precision. The exact quantity is critical. Water is measured with particular care. The water-to-cement ratio is fundamental to concrete quality. Chemical additives are measured in precise quantities, sometimes in milliliters. All materials are loaded into a massive rotating mixing drum. The drum is tilted at an angle. As it rotates, the materials tumble and mix. The sand and gravel become evenly coated with cement. The water is distributed throughout the mixture. Chemical additives that improve concrete properties are added. Plasticizers that improve workability, air entraining agents that improve durability, and various other additives that modify concrete properties. The mixing continues for 3 to 4 minutes. The operator watches the mix carefully, ensuring that all materials are combining properly. The finished concrete becomes a uniform gray or brownish mixture. The finished concrete is discharged from the mixing drum into a concrete truck's rotating barrel. The barrel is tilted to receive the concrete. As the barrel fills, it remains rotating to maintain uniformity. The truck operator verifies that the truck is completely full, no more and no less than the design capacity. The truck operator checks the ticket verifying the concrete mix design. The truck identification number is recorded. The delivery location is confirmed. The truck departs the batching plant heading toward the dam site. The concrete is delivered via truck to a central collection point at the dam site, sometimes tens of kilometers away. The journey must be completed within 1 to 2 hours. If the concrete begins to set before placement, it becomes difficult or impossible to work with. Set time is a critical constraint that limits delivery distance. The concrete is transferred from the truck into a large receiving hopper, a funnel-shaped device that collects concrete from arriving trucks. The concrete accumulates in the receiving hopper until sufficient volume is available for transport to the placement location. A conveyor belt system carries the concrete to the dam site, sometimes at multiple elevation changes. The conveyor system is substantial, wide enough to carry significant quantities continuously. The system is supported on a complex framework spanning the excavation. The conveyor belts are powered by electric motors, sometimes large motors rated in the hundreds of kilowatts. The belts move steadily, never stopping during working hours. Multiple conveyor levels are sometimes used, carrying concrete to different elevations of the dam. The system creates a dramatic sight, concrete flowing upward through the excavation on massive conveyor belts. The belts move at a steady pace, maintaining a constant flow of material. The sound is the mechanical rumble of the conveyor system, the hum of the electric motors, the rolling of the conveyor rollers, the flow of concrete on the belt. As the concrete reaches the placement location, it's discharged from the conveyor belt onto placement surfaces. Workers spread the concrete using hand tools and controlled spreading equipment. The concrete must be distributed evenly, no thick spots and no thin spots. The distribution must be complete, ensuring that no areas are left without concrete. Vibration equipment, mechanical vibrators lowered into the concrete, ensures the concrete consolidates properly. The vibrators buzz at high frequency, vibrating the concrete. The vibration allows the concrete particles to settle and rearrange, eliminating air pockets. Air pockets are undesirable, they reduce concrete strength and allow water penetration. The concrete placement is so voluminous that a new rhythm is established. As one section of concrete is being vibrated and finished, the next section is being filled from the conveyor. The process is continuous and methodical. The rhythm repeats day after day, week after week. Workers with laser levels verify that the concrete surface is at the correct elevation. Any high spots are worked down. Any low spots are filled. The precision is critical. The track system that will eventually be installed or the turbine installations require absolutely level surfaces. Curing is carefully managed. The concrete must cure in specific conditions to develop strength properly. The concrete generates heat as it cures. The chemical reaction between cement and water is exothermic. In massive dam structures, the internal heat can reach high temperatures, potentially causing cracks if cooling is not managed. Cooling systems may be employed, water-filled pipes embedded in the concrete that carry cool water. The water circulates through the pipes, absorbing heat from the concrete. The water is cooled at the surface and recirculated. The cooling extends the hydration period, allowing the concrete to strengthen gradually without excessive temperature rise. Weather protection systems are sometimes installed, temporary structures that provide shade or that provide protection from rain. The protection ensures optimal curing conditions. Direct sun can cause surface cracks. Rainfall can affect the surface quality. The rhythm of concrete production and placement becomes the heartbeat of the dam construction project. Every single day, new concrete is mixed, transported, placed, and consolidated. The dam grows layer by layer, section by section. The productivity is measured in cubic meters per day, with targets of 800 to 1,000 cubic meters being typical. With concrete being produced and delivered at massive scale, the actual dam structure begins to rise. The dam is not constructed all at once. Instead, it's built systematically, section by section, creating a massive three-dimensional structure that will eventually span nearly 2 kilometers. The dam foundation, the lowest section resting directly on bedrock, is constructed first. This foundation layer is absolutely critical. It must be absolutely solid, absolutely secure. Every ton of concrete that will be placed above the foundation will rest on this layer. The foundation must distribute the dam's weight evenly across the bedrock. Any weakness in the foundation could eventually lead to catastrophic failure. Concrete placement for the foundation is meticulous. The massive volume is placed in controlled layers. Each layer might be 5 to 10 meters thick. Each layer is placed carefully, with full attention to achieving complete coverage and proper consolidation. The placement of the foundation concrete takes weeks. The continuous rumble of conveyor belts, the vibration of consolidation equipment, the sound of workers communicating, these sounds blend together, creating the constant background noise of foundation construction. Once the foundation is sufficiently cured, typically 2 to 3 weeks after placement, construction of the main dam body begins. The dam will eventually be 180 meters tall. This height is achieved by stacking concrete in segments, layer by layer. A new layer of concrete is placed on the foundation. The concrete spreads across the width of the dam, nearly 2 kilometers in length. The thickness of each layer might be several meters. Conveyor belts deliver concrete at a steady rate. Workers ensure complete coverage. No areas are left uncovered. Proper consolidation is ensured through vibration. The placement of each layer takes days or even weeks depending on the volume to be placed. The layer is finished to a uniform surface, then allowed to cure before the next layer is placed. The progression upward is steady but never rushed. Layer 2 is placed on layer 1, layer 3 on layer 2. The dam gradually rises from the river bottom. What is initially a structure disappearing into the excavation gradually becomes visible above ground level. Months pass. The dam continues to grow. By the time 6 months of construction have passed, the dam has risen approximately 30 to 40 meters above the original ground level. By 1 year of construction, the dam has risen 50 meters or more. The structure is now visible from considerable distances. People in the surrounding region can see the growing dam. The sight of the growing dam is impressive and dramatic. The massive concrete structure extends across the entire river valley. The width is enormous, 2 kilometers. The height is increasing month by month. The scale and precision of the construction are remarkable. The dam's face is smooth and uniform, designed for maximum strength and minimum water seepage. Internal structures are built into the dam as construction progresses. Spillway conduits, large passages that will allow excess water to flow over the dam during periods of high water, are formed within the concrete. These are complex structures requiring precise positioning. Outlet works, large passages through which water can be released from the reservoir, are formed. These conduits must be positioned exactly as designed, neither too high nor too low. The conduits are formed using removable forms, temporary structures that establish the shape. Concrete is placed around the forms. Once the concrete has cured, the forms are carefully removed, leaving behind the hollow conduit. Placement of concrete around these complex internal structures requires careful coordination. The structures must be positioned exactly as designed. Concrete must be placed without damaging the structures. No voids can be left around the structures. All spaces must be filled with concrete. Equipment installation progresses alongside concrete placement. Penstock pipes, large diameter steel pipes that will carry water to the turbines, are positioned as construction progresses. The pipes must be positioned precisely and secured to the dam structure with brackets and supports. The pipes must be strong enough to withstand water pressure from hundreds of meters of water above. The construction progresses methodically upward. Year 2 of construction finds the dam at approximately 100 meters in height. The structure is now truly impressive. If a person stood at the base and looked upward, the top of the dam would be nearly out of sight, nearly 100 meters above. A 30-story building is approximately 100 meters tall. The dam is now as tall as a tall office building. The structure is now visible from dozens of kilometers away. The exposed concrete face is smooth and uniform. The dam's shape is elegant, wider at the base to handle the water pressure, narrower at the top. The shape is the result of sophisticated engineering calculations balancing strength requirements with economic efficiency. The rhythm of construction becomes almost meditative for observers. Each day brings new layers. Each week brings visible progress. The steady, relentless progress transforms the landscape. Workers who have been present from the beginning watch the structure rise from nothing to a massive monument of engineering. Approximately 3 years into construction, the dam structure reaches its final height. 180 meters of concrete rise from the river valley. The top of the dam is now accessible to workers and vehicles. A road runs along the top of the dam, connecting the construction areas. Nearly 3 million cubic meters of concrete have been placed, consolidated, and cured. The concrete weighs approximately 7.5 million tons. The mass of the structure is enormous. The force it exerts on the foundation is tremendous. But the foundation rock supports it because the engineering has been done correctly. The dam structure is complete. It has been constructed over approximately 3.5 years of continuous work. The final stages require meticulous finishing work. Any visible defects are repaired. The top surface is finished smoothly. The structure is ready for water to be impounded. The dam is more than just a solid barrier. It includes complex hydraulic structures that allow water to be controlled and released safely. The spillway is the primary safety feature. When the reservoir reaches its maximum capacity and water continues to flow into it, water must be released to prevent the reservoir from overtopping the dam and causing failure. The spillway is designed to safely carry away excess water without damaging the dam structure. The spillway on our dam is a gravity spillway. Water flows over the top of the dam, then cascades down the downstream face. The design is elegant and efficient. As water flows down the downstream face, it accelerates due to gravity. By the time the water reaches the base of the dam, it's traveling at tremendous velocity. The design of the spillway shape is critical. The surface must be smooth to minimize friction. The shape must guide the water away from the dam structure. The shape is determined through hydraulic modeling. Computer simulations and physical scale models test various designs before the final design is selected. Energy dissipators take various forms. Our dam includes a stilling basin, a large, specially shaped pool at the base of the dam where the water's kinetic energy is dissipated through turbulence and circulation. The basin is carefully designed based on hydraulic modeling that tests various designs before final construction. The stilling basin is constructed with precision. The shape is exact. Deviations from the design would reduce effectiveness. The concrete finish is smooth to minimize friction. The basin walls are reinforced to withstand the forces generated by the turbulent water. The outlet works are critical structures that allow water to be released from the reservoir for power generation and flow management. These are large diameter conduits, sometimes as much as 4 to 6 meters in diameter, that pass through the dam and open into the river downstream. The outlet works include intake structures at the elevation where water will be drawn from the reservoir. These intakes are carefully designed to minimize debris entry. Trash racks, barriers that prevent logs and other debris from entering the system, are installed. The racks must allow free water flow while preventing debris passage. The intake structures are positioned at a specific elevation determined by engineering analysis. If the intake is too high, insufficient water can be drawn during low water conditions. If the intake is too low, sediment and debris are drawn into the system. The correct elevation balances these considerations. The intake structure opens into large conduits that pass through the dam. The conduits slope downward, allowing gravity to drive water through the system. The conduits are lined with concrete or, sometimes, with special materials that reduce friction and wear. Penstock pipes that carry water to the turbines are massive steel structures. The pipes must be extremely strong to withstand the pressure of water. The water pressure at the bottom of a 100-meter column of water is approximately 10 atmospheres, 10 times atmospheric pressure. Deeper reservoirs create even greater pressures. The penstock installation is meticulous work. The pipes are positioned on supports that allow for thermal expansion. Steel expands and contracts with temperature changes. The support system must allow these movements without creating stress on the pipes. The pipes are tested extensively to ensure they can withstand the intended pressure without leaking. Any flaw, a crack, a poorly sealed joint, a material defect, could lead to catastrophic failure. High-pressure water would force through the flaw, enlarging it progressively until the pipe failed completely. Testing is performed using pressurized water. The pipe is sealed at both ends. Water is pumped in under pressure. The pressure is gradually increased until it reaches the maximum operating pressure. The pipe is held at this pressure for an extended period. If no leaks develop, the pipe passes the test. Penstock test complete. Maximum pressure, 120 atmospheres. No leaks detected. Pipe approved for service, a technician reports. Gate structures are installed in the outlet works and spillway. These are massive machinery pieces capable of starting and stopping water flow. The gates can range from simple stop logs, removable wooden or steel beams stacked to block flow, to sophisticated mechanical gates operated by hydraulic or electric motors. The gates must operate smoothly and reliably. They must be able to stop water flow in seconds if necessary. They must seal completely to prevent water leakage when closed. Gate testing involves raising and lowering the gates repeatedly, monitoring their smooth operation. The gates are operated at various speeds. The seal is tested by applying water pressure against the closed gate and verifying that no water leaks past the gate. Gate 1 raised at normal speed. No binding. No resistance. Operation smooth. Gate 1 lowered. Seal tested with water pressure. No leakage. Gate 1 approved for service. The spillway surface is finished to minimize erosion. The concrete is smooth as can be practically achieved. The finishing is done using specialized equipment and techniques. The goal is to create a surface that water can flow over without creating erosion. Concrete coating may be applied for additional protection. Special coatings improve wear resistance and durability. The coating must be smooth and durable. It must not flake or deteriorate under high-velocity water flow. The heart of a hydroelectric facility is the turbine, the mechanical device that converts flowing water's energy into rotational motion. The turbine must be specifically designed for the water pressure, water flow rate, and elevation characteristics of this particular dam. Turbine design is a sophisticated process. Engineers use computational fluid dynamics, sophisticated computer simulations, to model water flow through the turbine. Various blade designs are tested computationally. The design that produces maximum efficiency is selected for manufacture. The turbine house, a large building carved partially into the rock adjacent to the dam, is being excavated and finished. This is where the turbines and generators will be installed. The turbine house is underground or partially underground for several reasons. It provides protection from the elements, it reduces noise transmitted to the surface, and it simplifies the penstock routing from the dam to the turbine. The turbine room is an impressive underground chamber. Large turbines, sometimes 5 to 7 meters in diameter, will be installed here. The turbines are custom manufactured devices, manufactured specifically for this dam. Each turbine is essentially unique, designed for the specific conditions of this facility. The first turbine arrives at the site. It's transported on a special heavy-haul truck, carefully secured to prevent movement. The turbine is so large and heavy that special transportation routes and permissions are required. The truck driver must navigate carefully around curves and over roads that can support the weight. The turbine is moved into the turbine house using overhead cranes. Positioning requires millimeter-level precision. The turbine must align perfectly with the penstock that supplies it and with the draft tube that carries water away from it. Any misalignment would cause vibration and accelerated wear. Workers spend weeks positioning the turbine. Measurements are taken continuously. Laser alignment tools are used to verify alignment. Slight adjustments are made millimeter by millimeter. Finally, when the turbine is perfectly positioned, it is secured in its final location. The turbine is a marvel of mechanical engineering. The rotor, the rotating part, contains curved blades that direct the water flow. The water strikes the blades, forcing the rotor to spin. The rotor spins at tremendous speed, sometimes 200 to 300 revolutions per minute depending on the turbine type. The generator is positioned next to the turbine. The generator is a large electrical machine that converts mechanical rotation into electrical current. The generator contains a coil of wire positioned in a magnetic field. As the coil rotates, driven by the rotating turbine, electrical current is generated. The generator is connected to the turbine through a gearbox. The gearbox changes the rotational speed. The turbine rotates at one speed, but the generator must rotate at a different speed to generate electrical current at the correct frequency, typically 50 or 60 Hz depending on the region. All three components, turbine, gearbox, and generator, must be perfectly aligned. Laser alignment tools are used to verify alignment to within fractions of a millimeter. Misalignment would cause vibration and accelerated wear. The alignment process takes considerable time and effort. Turbine gearbox generator alignment complete. Radial alignment verified to within 0.05 millimeters. Angular alignment verified to within 0.01 degrees. Installation approved. Electrical systems are connected to the generator. Large cables carry generated electricity from the generator to transformers. The cables must be sized to carry the electrical current without overheating. The cables are insulated to withstand the voltage. Multiple turbines and generators are installed in sequence. Turbine 2 follows Turbine 1. Turbine 3 follows Turbine 2. Our large dam will eventually have 4 turbine generator units. Each unit is installed with identical care and precision. The work is meticulous and time-consuming. Each unit takes weeks or months to install, align, and test. Testing of turbine systems begins without water flow. The mechanical systems are operated to ensure smooth rotation and absence of binding. The rotor is spun to verify that it rotates freely. The bearings are checked. They should rotate smoothly with minimal noise. The generator is tested to confirm proper electrical generation. The generator is mechanically rotated, and electrical output is measured. The output should be 0 volts when rotating at low speed, gradually increasing as rotation speed increases. All systems are verified to operate correctly before water is actually allowed to flow through the turbines. Running a turbine with water for the first time is potentially dangerous. If problems exist, they'll manifest immediately at high pressure. The mechanical testing ensures that problems are identified and corrected before water introduction. The electricity generated by the hydroelectric facility must be transmitted to cities and communities where it will be used. This requires a complex electrical transmission and distribution system extending for considerable distances. Transformers are massive electrical devices that step up the generator voltage to very high levels suitable for long-distance transmission. A generator might produce electricity at 10,000 volts. For long-distance transmission, this must be stepped up to 100,000 volts or higher. The transformation reduces electrical losses during transmission. Transformer installation requires careful work. The transformers are heavy, some weighing hundreds of tons. They must be positioned precisely and connected correctly. Any incorrect connection could cause failure or even explosion. Electrical testing of transformers is thorough and systematic. High voltage tests verify that the transformers can handle the voltages they'll experience in service. Efficiency tests confirm that the transformers minimize energy loss. All tests must be passed before the transformers are placed into service. Large transformer yards are constructed adjacent to the dam. Multiple transformers handle the output from multiple turbines. The yard is a forest of large electrical equipment. Transformers standing on concrete pads, switching gear, control systems, measurement equipment, all interconnected with large electrical cables. The transformer yard is a dangerous environment due to the high electrical voltages present. Safety protocols are strict. Only trained personnel are allowed in the yard. Electrical hazard warnings are posted. Proper electrical safety equipment, insulated tools, protective clothing, is required. Transmission towers are constructed extending from the dam site toward distant cities. These towers are massive steel structures, sometimes as tall as 100 meters, spaced approximately 500 meters apart. The towers must be strong enough to support the transmission lines in all weather conditions: high wind, heavy snow, ice accumulation. The transmission lines themselves are strung between the towers with care and precision. The lines are large diameter aluminum conductors, sometimes as thick as a person's arm. The lines must be at the correct sag, not too tight, not too loose. Tension is carefully monitored as the lines are installed. Proper sag is critical. If lines are too tight, thermal expansion during hot weather could break them. If lines are too loose, they could sag into obstacles or other lines. The sag is calculated based on the temperature at installation and adjusted for different weather conditions. Insulators are attached to the towers, isolating the high voltage lines from the towers themselves. The insulators must withstand voltages of several 100,000 volts. The insulators are typically ceramic or composite materials that provide excellent electrical insulation. The transmission line installation is coordinated carefully. The lines are pulled into position using mechanical tensioners. Workers guide the lines onto the insulators. The process is slow and methodical. The entire process of stringing transmission lines across hundreds of kilometers takes months. Control systems are installed at the dam and at substations where power is distributed to the grid. These systems automatically regulate the electrical generation to match demand. Sensors measure electrical load throughout the distribution system. Computers analyze this data and adjust the water flow through the turbines to produce the correct amount of electricity. If electrical demand increases, for example, when air conditioning is running during hot summer days, the control system opens water gates to allow more water through the turbines, increasing power generation. If electrical demand decreases, for example, late at night when most people are asleep, the control system reduces water flow, reducing power generation. The electrical system is tested extensively. Systems are operated without full load to ensure proper function. The protective systems that disconnect turbines if problems develop are tested. The emergency shutdown systems are tested. Loads are gradually increased, testing the system's ability to handle increasing power demand. Electrical system energized. Generator output increasing in stages. 100 megawatts, 200 megawatts, 300 megawatts. All parameters normal. System performing within specifications. By completion of this phase, the hydroelectric facility is fully operational from an electrical perspective. Electricity is being generated and transmitted to the grid. The moment of truth arrives. The reservoir is allowed to fill. The diversion structures are gradually closed. Water that previously flowed around the dam site is now allowed to flow toward the dam and accumulate behind it. The filling process is deliberate and controlled. Water gates are slowly moved to position. The diversion flow is gradually reduced. More and more water flows toward the dam site and begins to accumulate behind the dam structure. The water level begins to rise. The rising water is monitored continuously. Instruments at multiple locations measure water level with precision. Settlement of the dam is carefully monitored. As water pressure increases, the dam may settle slightly. Settlements must remain within acceptable limits. If settlement exceeds acceptable limits, the filling is halted until the problem is investigated. Water level at 30 meters above baseline. Dam settlement, 18 millimeters. All values within acceptable ranges. Continuing water impoundment, an engineer reports. The water rises day by day. What was a dry riverbed is becoming a lake. The surface area of water gradually expands as the level rises. Water covers land that has been dry for millennia, transforming the landscape. Vegetation is submerged. Wildlife evacuates or adapts. The ecological transformation is dramatic. What was forest or grassland becomes aquatic environment. Fish and aquatic plants now inhabit waters that didn't exist weeks before. Water flow into the reservoir is monitored carefully. The rate of rise is controlled. If water rises too quickly, internal pressures could become problematic. The stress on the concrete could exceed design limits. Managers sometimes reduce water inflow to prevent excessive rate of rise. Dam behavior during filling is critical. Cracks might develop if the dam experiences excessive stress. The concrete isn't monolithic, it's poured in sections. The joints between sections might open if stress is excessive. Monitoring equipment continuously measures movements and stresses. The water continues to rise. 50 meters, 60 meters, 70 meters. The water surface becomes larger with each rising meter. The volume of water accumulating is enormous. Eventually, the reservoir will contain tens of billions of cubic meters of water. The rising water is momentarily diverted to test spillway function. Water is allowed to flow over the spillway in controlled amounts. The spillway operates smoothly, carrying water away from the dam safely. The design has proven correct. Emergency spillway testing occurs. Even larger quantities of water flow over the spillway. The structure handles the flow without damage. The spillway design has proven capable of handling extreme flows. Spillway test at 50% design capacity. Flow smooth, stilling basin functioning perfectly. No damage observed. Spillway approved for operation. By the time the water level reaches 120 meters, the eventual target level, the reservoir has become a vast inland lake. 40 kilometers of water extend upstream from the dam. The landscape has been transformed completely. What was a river valley is now a lake with irregular shorelines following the terrain. The reservoir is now operational. Water stored during high-flow seasons can be released during low-flow seasons, maintaining steady river flow year-round. The reservoir provides flood control. Excessive water from storms can be stored, preventing downstream flooding. The reservoir provides water for irrigation and drinking water supply. With the reservoir filled and systems tested, electrical generation begins. Water is allowed to flow from the reservoir toward the turbines. The first flow through the system is carefully controlled. A small amount of water is allowed to flow through one turbine. Engineers monitor the turbine's response carefully. Rotation speed is measured. Vibration is measured. Electrical output is measured. Water flow at 5% of design capacity. Turbine rotation at 150 RPM. Vibration levels minimal. Generator output steady at 30 megawatts. Systems operating normally. Water flow is gradually increased. 10% of design capacity. 20%. 30. The turbine accelerates smoothly. The generator output increases proportionally. The sound of the turbine increases, a low-frequency whine as the turbine spins faster. Water flow at 40% of design capacity. Turbine rotation at 500 RPM. Vibration levels normal. Generator output at 200 megawatts. System operating normally within parameters. When water flow reaches 100% of design capacity, the turbine is operating at its nominal speed. The electrical output is at its design value, perhaps 400 to 500 megawatts per turbine. Multiple turbines operating simultaneously deliver over 1,000 megawatts to the electrical grid. Water flow at 100% of design capacity. Turbine rotation at 800 RPM. Electrical output at 470 megawatts. All parameters nominal. The operation becomes routine. Water flows continuously from the reservoir toward the turbines. The turbines rotate steadily. The generators produce electricity continuously. Power flows through transformers to transmission lines. The transmission lines carry power to distant cities where it lights homes and powers industries. Operators in a control room monitor the system continuously. Electronic displays show water pressure, turbine speed, electrical output, and numerous other key parameters. Alarms alert operators to any anomalies. But routine operation rarely produces surprises. The systems are designed to operate automatically under normal conditions. The facility operates 24 hours per day, 7 days per week. The only interruptions are scheduled maintenance and occasional equipment failures requiring repair. Water management is continuous. During high-flow seasons when rainfall is abundant and river flow is high, excess water flows over the spillway. During low-flow seasons, water is released from the reservoir to maintain river flow. The electrical output varies with water flow and with electrical demand. During peak hours when electrical demand is high, more water flows through the turbines, producing more power. During off-peak hours when demand is lower, less water flows. Maintenance of the facility is ongoing. Bearing inspection occurs at regular intervals. Oil analysis is performed to detect wear. Mechanical seals are inspected. Any signs of wear are addressed during scheduled maintenance windows. The turbines require periodic maintenance. After several years of operation, the turbine blades may show erosion from the water flow. The blades are examined using ultrasonics or other inspection methods. If erosion is significant, the turbine is removed for refurbishment. The turbine blades are replaced or resurfaced. The turbine is reinstalled and tested before return to service. The generators are equally subject to maintenance. Bearing condition is monitored. Winding insulation is tested. Any degradation triggers maintenance action. Modern generators can last for 50 years or more with proper maintenance. The dam and reservoir are not simply structures that generate electricity, they're complex systems that manage water resources for multiple purposes. The management requires constant attention and sophisticated decision-making. Water management begins with understanding water availability. Hydrological monitoring stations upstream of the reservoir measure river flow continuously. This data is analyzed to predict future water availability. Computer models forecast water flows for the next weeks and months based on current conditions and historical patterns. During the wet season, when rainfall is abundant and river flow is high, the reservoir may rise toward its maximum level. The managers must make decisions about how much water to release. How much should be stored for future use? How much should be allowed to flow downstream? These decisions balance multiple objectives. Power generation, which benefits from maximum water flow through turbines, downstream irrigation needs, which need a certain minimum flow, flood control, which requires some reservoir space available for incoming water, environmental flows, minimum flow needed to support ecosystems, water supply, water needed for drinking and industrial uses. During the dry season, when river flow is naturally low, water stored in the reservoir becomes the primary source of river flow. Releases from the reservoir maintain minimum flow levels that support ecosystems and allow downstream water users to draw water. The decisions are complex and require judgment. Incorrect decisions can have serious consequences. If too much water is released during the wet season, there might not be sufficient storage available when flooding occurs. If too little water is released during the dry season, downstream agricultural and water users might suffer water shortages. Water stored for irrigation is released according to agricultural demand. In the agricultural season, farmers need water for crop irrigation. The dam releases are adjusted to provide this water. In the off-season, less water is needed for irrigation. Current demand from irrigation system, 200 cubic meters per second. Releasing water at 200 cubic meters per second to satisfy demand while maintaining downstream minimum flow of 100 cubic meters per second. Flood management occurs when storms bring excessive precipitation. The reservoir is prepared to capture floodwaters by maintaining space below the maximum level during flood season. When a flood event occurs, the reservoir captures water that would otherwise flood downstream areas, preventing damage to communities and agriculture. The flood management capability of dams is sometimes underappreciated. A single large reservoir can prevent billions of dollars of flood damage. The prevention is invisible. People don't see the floods that don't happen because the dam captured the water. Environmental flows are carefully managed. Rivers have ecological needs. Fish need certain flow rates to migrate. Aquatic plants need certain conditions. The dam operations are adjusted to provide these environmental flows, even when power generation and irrigation might benefit from different releases. Environmental flow requirement: minimum 150 cubic meters per second to maintain fish spawning habitat. Current release: 150 cubic meters per second, maintaining environmental minimum. Sedimentation management is an ongoing consideration. Rivers naturally carry sediment, sand and silt eroded from upstream areas. When the river's flow slows in the reservoir, sediment settles to the bottom. Over decades, sediment can accumulate, reducing the reservoir's capacity to store water. Our dam includes sediment management systems. Periodically, sediment accumulated in certain areas is flushed out. Large volumes of water are released rapidly, resuspending the sediment and carrying it downstream. This maintains the reservoir's long-term capacity. Water quality monitoring is continuous. The water in the reservoir is analyzed for various chemical and biological parameters. Temperature, dissolved oxygen, pH, and nutrient levels are measured. Any problems are identified quickly and addressed. Temperature management is sometimes necessary. Water drawn from the bottom of a deep reservoir can be very cold. This cold water might be unsuitable for some downstream users. Temperature control systems sometimes allow water to be drawn from different elevations to achieve an appropriate temperature. Temperature of water at intake level: 4 degrees Celsius. This is too cold for downstream irrigation users. Adjusting intake position to draw water from elevation with higher temperature. The operational complexity of dam management is remarkable. Operators must balance multiple objectives while responding to variable natural conditions. The complexity is managed through sophisticated monitoring systems, computer models, and operator expertise. The construction and operation of a large dam have profound environmental and social impacts. Managing these impacts is an integral and ongoing part of dam operations. Fish passage is a critical concern. Many fish species migrate up and down rivers seasonally to spawn and feed. The dam blocks these migrations. Modern dams include fish passage systems that allow fish to move past the dam. A fish ladder is a series of ascending pools separated by small waterfalls. Fish swim from one pool to the next, gradually ascending over the dam. The design is based on fish swimming behavior. The pools are sized and spaced to accommodate the fish's jumping ability. Fish passage effectiveness is monitored continuously. Counting systems measure how many fish successfully pass the dam in each direction. Video cameras record fish behavior, allowing biologists to assess passage effectiveness. If passage rates are low, the system is adjusted. The water flow pattern is modified, or the ladder design is enhanced. Fish ladder efficiency this month, 82%. This exceeds our target of 75%. Fish populations upstream of dam are recovering well. On the downstream side of the dam, fish passage systems allow fish to bypass the dam and continue downstream. These bypass systems are critical for fish species that need to migrate downstream to ocean feeding grounds. The bypass systems are sophisticated. Some use screens to guide fish, others use behavioral responses to guide fish toward the bypass entrance. Habitat restoration is ongoing. Areas that lost habitat due to reservoir impoundment are compensated through habitat creation elsewhere. Wetlands are created on previously upland areas. Native vegetation is replanted on disturbed areas. Wildlife corridors are established. Habitat restoration program has created 5,000 hectares of new wetland habitat over past 5 years. This compensates for habitat lost to reservoir impoundment and has expanded overall wetland area and region. Sediment-related issues are managed proactively. The sediment trapped behind the dam would naturally flow downstream, providing nutrients and building river deltas. Without this sediment, downstream areas may be depleted. Our dam manages this through periodic sediment releases. Water temperature changes are managed. The cold hypolimnion water released from deep in the reservoir can dramatically change the temperature of the river. This temperature change can harm aquatic ecosystems. Selective withdrawal systems, mechanisms that allow water to be drawn from different reservoir depths, help manage temperature by drawing water from warmer or cooler elevations as needed. Hydropower development typically displaces communities. The reservoir inundated settlements and agricultural areas. Our dam required relocation of approximately 30,000 people, a substantial social impact. The resettlement process is complex and sensitive. Resettlement involves fair compensation for lost land and property. It also involves cultural adaptation. Communities must establish themselves in new locations. New schools and hospitals are built in resettlement areas. Marketplaces are established where commerce can occur. Religious sites that cannot be moved are documented through photography and detailed documentation, preserving cultural memory. Resettlement program is 50% complete. 3 major communities have been relocated. 8,000 families have received fair compensation and resettled in new locations with adequate housing and facilities. Social cohesion, the bonds between community members, must be re-established. The government supports community development programs. Education and livelihood training help residents adapt to changed circumstances. The resettlement is managed with sensitivity to cultural factors. Traditional practices are supported in the new locations. Efforts are made to minimize psychological trauma associated with displacement. Economic impacts extend broadly. The dam creates employment during construction, 20,000 jobs at peak construction. It creates permanent employment in operations and maintenance, 500 jobs. It provides reliable electricity that supports economic development downstream. Industries can locate with confidence in power availability. It provides water for irrigation that supports agriculture. The local economy around the dam develops. Towns grow near the dam to serve the facility. Tourism develops. The reservoir becomes a recreation site. Fishing, boating, and water sports provide economic activity and employment. Recreation management is important. The reservoir becomes a valuable recreation resource. Beaches are developed on suitable shoreline areas. Boating areas are designated. Fishing areas are established. Recreation area at Northern Reservoir location has become major tourist destination. 10,000 visitors monthly during summer season. Local businesses have grown substantially. Revenue to local government from recreation concessions, $5 million annually. Environmental monitoring continues indefinitely. The long-term effects of the dam are studied systematically. Ecological changes are documented. Fish populations are monitored, both upstream and downstream of the dam. Water quality is tracked continuously. A hydroelectric dam can operate reliably for 100 years or more. Long-term maintenance and continuous improvement are essential to ensure continued reliable operation. Concrete inspection is ongoing. Although concrete is durable, it's not permanent. Cracks may develop over time. Weathering occurs over decades. Regular inspection detects any problems before they become serious. Divers inspect underwater portions of the dam and intake structures. The work is meticulous and challenging. Working at depth requires specialized training and equipment. The inspections examine concrete surfaces for cracks, erosion, or deterioration. Underwater inspection of dam foundation completed. Minor surface weathering observed but no structural cracks detected. Foundation integrity excellent after 10 years of operation. The penstock pipes that carry water to the turbines are inspected regularly. The pipes are opened periodically, and inspection equipment is inserted to examine the interior surfaces. Any corrosion or damage is documented and repaired. Mechanical components are maintained on strict schedules. Bearing replacements occur at defined intervals, typically every 10 to 15 years. Seal replacements maintain water tightness. Turbine blade inspection occurs regularly. Any erosion or damage is addressed. Erosion of turbine blades is inevitable. Water flowing at high velocity gradually wears the blade surfaces. After several years of operation, blade erosion becomes significant. The turbine is removed from service temporarily. The blades are replaced or resurfaced. Modern blade materials are more erosion resistant than older designs. Turbine Unit 2 removed from service for blade resurfacing. Inspection shows typical erosion pattern for 10 years of operation. Blade surfaces will be resurfaced to restore efficiency. Turbine will return to service within 2 months. Gate mechanisms are exercised regularly. The large gates that control water flow are operated periodically to ensure smooth operation. If a gate begins to stick or bind, maintenance is scheduled immediately. Gate operation test completed on spillway gates 1 through 4. All gates operate smoothly. No binding or resistance. Gates approved for continued service. Electrical systems require continuous maintenance. Transformer oil is analyzed periodically. The oil provides both cooling and insulation. If analysis shows degradation, the oil is replaced. Electrical connections are inspected. Any corrosion is removed and the connection is resealed. Sediment management continues throughout the facility's life. As sediment accumulates behind the dam, its volume and composition are monitored. Advanced measurement techniques determine the sediment volume in various areas of the reservoir. If sediment becomes problematic, mechanical cleaning or flushing may be performed. Annual sediment survey shows 300,000 cubic meters of sediment accumulation during past year. This is within normal range. Sediment management program is functioning effectively. Reservoir sedimentation rate, 0.4% per year. Spillway maintenance involves repair of any erosion or damage. The spillway surface is inspected regularly. Any cracks are repaired before they can grow. The spillway must remain in excellent condition to safely handle future floods. Safety systems are tested continuously. Emergency spillways are operated regularly to ensure function. Spillway gates are exercised. Automatic control systems are tested to ensure proper response to emergency conditions. Emergency spillway test conducted successfully. Gates operated smoothly. Flow diverted correctly. System ready for emergency operation if needed. Dam safety reviews occur periodically. Independent engineering firms audit the facility. Engineers with expertise in dam safety analyze all aspects of dam operation. Recommendations for improvements are implemented. The operation becomes increasingly routine with time. The facility operates with minimal human intervention. Modern systems are highly automated. Operators monitor displays and respond to alarms. Most operation is automatic and controlled by computers. The facility's efficiency improves with optimization. Operating procedures are refined based on decades of experience. Small changes in procedures can significantly improve overall performance. Water release patterns are optimized. Turbine operations are fine-tuned. The power generation continues year after year, decade after decade. The facility becomes part of the region's infrastructure, so reliable that its operation is taken for granted. People flip light switches and use electricity without thinking about the hydroelectric facility that may be providing that power. A hydroelectric facility provides resilience to water-stressed regions and helps communities adapt to climate-induced changes. During drought periods, the dam's stored water becomes invaluable. Surface water sources dry up. Groundwater becomes depleted. The reservoir provides reliable water supply when natural sources fail. The water is used for irrigation, drinking water supply, and power generation. Current drought conditions show precipitation 70% below normal. Natural river flow at historical low. Reservoir providing 90% of water supply. Without reservoir, region would face severe water shortage. Climate change impacts water availability profoundly. Changing precipitation patterns alter water flows. Glacial melting changes seasonal patterns. A well-managed reservoir helps communities adapt. Water can be stored during unexpectedly high flow periods and released during low flow periods. The dam reduces vulnerability to both floods and droughts, two extremes of water availability. Flood capacity protects against excessive water. Stored water protects against water scarcity. The electricity generated by the dam is clean and renewable. Unlike fossil fuel power plants, the dam produces no greenhouse gas emissions during operation. This clean power contributes directly to climate change mitigation. Hydroelectric generation during past year, 8,000 gigawatt-hours. Greenhouse gas emissions avoided, 4 million metric tons. Carbon dioxide equivalent reduction equivalent to removing 800,000 automobiles from service for 1 year. The reservoir's surface acts as a water storage mechanism that evens out seasonal variations. Instead of water flowing to the sea in high-flow seasons and being scarce in low-flow seasons, the reservoir captures excess and releases during scarcity. Land use downstream of the dam is more stable. Flooding is reduced, allowing more stable agricultural and urban development. Communities can grow and thrive without fear of catastrophic flooding. Downstream flooding eliminated in region. Previously, major floods occurred approximately once every 5 years, causing widespread damage and loss of life. Since dam construction, flooding has been controlled. Economic productivity of agricultural land has increased substantially. The dam's existence creates environmental constraints. Ecosystems must adapt to new water flow patterns. Some species benefit, others decline. Fish migration patterns change. The balance of species changes permanently. But the dam's existence also enables ecosystem restoration in some cases. Water released during dry seasons maintains minimum flows that support aquatic life that would otherwise disappear. The dam can be managed to mimic natural flow patterns. Long-term water availability allows agricultural development that would be impossible without the dam. Irrigation systems are constructed, creating stable food production even during dry years. Rural economies develop around irrigation-based agriculture. Irrigated agricultural area downstream of dam, 500,000 hectares. Food production supporting population of 3 million people. Agricultural productivity increased 150% since dam construction due to reliable water availability. Water security, reliable water supply, is a foundation for regional development. The dam contributes to this security, enabling demographic growth and economic development. The facility becomes increasingly valuable over time as water becomes more precious and climate becomes more variable. The dam's strategic importance increases with each passing year. After years of exhaustive study, construction spanning 3 to 4 years, and then decades of successful operation, a hydroelectric dam becomes an integral part of regional infrastructure. The facility quietly performs its functions, generating electricity, managing water, preventing floods, supporting irrigation, and providing recreation. The transformation from proposal to reality is remarkable. From the early surveys through environmental assessments, through years of construction with thousands of workers, through commissioning and decades of operation, the dam journey is lengthy and complex. The legacy of the dam extends far beyond the initial design intent. The reservoir becomes a recreation resource where tens of thousands of people enjoy boating, fishing, and water sports annually. The facility provides educational opportunities for students learning about hydropower and water management. The facility becomes a symbol of engineering achievement and human capability. The dam serves multiple generations. People born after the dam's completion grow up using the electricity it produces. They drink water stored in the reservoir. They fish in the reservoir. They use irrigation water for crops. They visit the reservoir for recreation. The dam is simply part of their world. The facility eventually requires major rehabilitation. After 50 to 100 years of operation, major components may need replacement. The penstock pipes may need replacement due to corrosion. Turbines may be upgraded to more efficient modern models. Concrete may require repair or protective measures. Rehabilitation involves careful planning. The facility cannot simply be shut down for years. It's too important to the region's power supply. Rehabilitation occurs in phases, maintaining power generation while work progresses. New generators using updated technology replace old ones. The efficiency improves, allowing more power generation from the same water flow. The facility becomes more valuable economically. The dam joins an infrastructure ecosystem, bridges, power plants, water treatment facilities, roads, that collectively enables modern life. Each facility depends on others and contributes to the whole. The lessons learned from dam construction apply to future projects. The expertise of engineers and workers is preserved and transmitted to future generations. The knowledge builds, allowing better future projects. The environmental lessons are equally important. Future dams incorporate better environmental management. Fish passage is improved. Ecosystem considerations are better integrated from the project's beginning. The dam stands as a testament to human capability to envision solutions to complex problems and execute the engineering to make those solutions real. The dam stores water, prevents floods, generates electricity, supports agriculture, and enables economic development, all functions that improve human welfare. As we conclude our 160-minute journey through comprehensive dam construction and operation, reflect on the transformation. What begins as a river flowing unremarkably through a valley becomes a managed water resource, a power generation facility, a flood control system, an ecosystem of complexity and significance. The dam will stand for centuries. Future generations will depend on the electricity and water the dam provides. The engineering excellence represented by the dam will inspire engineers for generations to come. Sleep now, knowing that the world's water resources are being managed through engineering of remarkable sophistication. The dams hold back floods. They store water during times of plenty for use during times of scarcity. They generate clean electricity that powers modern civilization. The dam represents achievement, human capability applied to solve problems and enable flourishing. The rhythm of water flowing, the steady generation of electricity, the careful management of resources. These represent progress and the application of human ingenuity to serve human needs.